All right, can I get a quick thumbs up on the camera if you can hear me? Okay, cool. Just want to make sure. Cool. So let's get started here. Today we're going to be going over, we have a little project, and we're going to be going over object-oriented programming as a paradigm. Today's class, we don't have slides or notes, so it's just a code along. And I have a kind of a structured project that I'm just going to talk about while I implement. And the expectation is for you to code along and try to get your code working, ask any questions that you have along the way. Feel free to do that. So what we're going to be doing is building just a couple classes, which are Python's way of building objects. You might have heard of objects before. We've used that term. So we can build our own custom objects with classes, and we're going to build a few classes. One's just going to be a simple class. It'll be sort of a minimal class with just minimal features, and yeah, just to kind of show you what a class is in a very basic sense. And then the other two will be sort of more formal object-oriented classes. And I'm going to kind of try to take this idea of like distinguishing like a class, using a class or building an object from like formal object-oriented programming. Some people say, well, if you're using classes, then you're doing object-oriented programming, and the two aren't quite one and the same. So I want to partly make that part clear. So keep that in the back of your mind. We'll be focusing kind of on object-oriented programming. This is probably a term you've heard before. Oh, excuse me, let me just, yes, okay. This is probably a term you've heard before. Object-oriented programming is what's called a programming paradigm. When we use that term, we're talking about a programming paradigm. So we're going to look at some features that we haven't covered yet, namely class and some of the features within class. But mostly, it's going to be a pretty familiar set of tools. You know, you still have to do the same things. Although, you know, the particulars of the way you do it are the paradigm. That's the paradigm, right? So you still need to encapsulate logic, abstract logic, which is what we've been doing with functions. You still need to repeat parts of your code, have repetition, iteration, which is what we've been using loops for. And you still need to write conditional logic, which is what we've been using if else for, and you still need to manipulate data types. We're going to be technically creating our own data types as well today. So you still need to do the basic things in any paradigm, and there are a variety of paradigms. Object-oriented programming is, in some ways, there's a lot of similarity to procedural programming or imperative programming, which is the paradigm that I've taught you thus far. We've done a style of procedural or imperative programming. So whether you knew that that's the paradigm that we were working out of or not, that's generally, I think, where most programming pedagogy starts, is with procedural imperative programming. And we choose to start there because it's a soft landing point, and it's generally sort of a simple set of tools that's fairly straightforward. So object-oriented programming is a bit, there are going to be some similarities, and there are going to be some differences. So just watch out for those, and feel free to ask if you have questions regarding that. So let me see if I can kind of encapsulate this in short, and then we'll sort of leave that to percolate as we go through this to the class. So the idea with object-oriented programming is you use objects. An object is an encapsulation of both what we call state and logic. So state has you think about it as something that has a value. It has a given state. maybe you don't know what that state is at that time, but it has state. At any given time, it has a state. Logic is a set of operations to complete a task. What you might think of as an algorithm. So we think about like functions as logical and things like variables as a state, and then loops and conditions are just things you implement for logic. They're just tools in logic, right? So objects encapsulate, they're like containers, and they're used for modularity and modules in Python and other languages. They're like containers that hold both stateful elements and logical elements, and they can sort of co-influence each other, right? You can have state that's set in a certain way, and then you can run some logic that's going to alter or utilize that state in some way, and they can kind of interact. The logical components are allowed to set and mutate the stateful components, and set, mutate, and reference, I should say. So you can read a stateful value, which is like a reference, where you're not altering it in any way. You're just saying, hey, what's the state of this particular part of the object? But in formal OO, it is okay for essentially your functions to reference and mutate variables outside of them, which, if that sounds familiar, it's because I've been telling you to this point not to do that. And you might ask, why does object-oriented programming center around this thing that I've been telling you not to do? And it's not just, it is my opinion, but it's not, it's a pretty widely held industry opinion to not write functions that reference or mutate values that are not either passed in as parameters or local to the function. It's a pretty commonly accepted idea, but this is a feature that object-oriented programming, which is, you could argue, the most dominant, or one of the most dominant paradigms in the industry, relies on. And so you might ask, why the contradiction? It's part of the mess. You know, it's I don't have a good answer to like why there's this well-established norm of not doing something, and then why the dominant paradigm sort of relies on doing that thing. There is a contradiction there. If you have a good answer as to why those two things can coexist, let me know. But yeah, so this is a bit of a breach of some sort of norms that I've gone over, that I've taught you guys, and that's okay in the context of object-oriented programming. There's a few little differences, but we'll kind of get into that. Cool. All right. So I just wanted to give a quick note on what we were talking about. All right, so classes. Let's look at a basic class. Let's build out a basic class. I covered this. So let's build out our first class. So our project today, what we really want to build up to is like a binomial distribution class, right? So we're gonna build out some logic for our binomial distribution into its own class, and we'll see why that's useful in a little bit. We'll be able to like retain, the state of a given distribution at a given point and alter it with its various methods, and we'll look at that. We're also going to build a Poisson class. Now, binomial and Poisson share some common tools. In both cases, we need factorial. in both cases, yeah, I mean, or in other cases, like we might need, multiple distributions will and various other things other than distributions will take advantage of things like permutations and combinations and factorial, things like that. So it would make sense, rather than building those tools from scratch for binomial and Poisson, it makes sense to build those tools externally and have those classes utilize the external tools. So I'm just going to make a class called stats tools. And the way we do that, we'll just say class, C-L-A-S-S, stats tools, and just a colon right there will do. And then from here, like I said, this is a container for logical and stateful elements, right? So for our binomial distribution and our Poisson distribution, we'll need factorial. And we'll just build out a few different statistics tools and things in this and kind of look at this. So let's start with factorial. So we'll have factorial takes in n, and we'll say prod equals 1 for I in range 1 to n plus 1. We'll say prod times gets I. And we'll return prod. Okay, cool. So we wrote our factorial function. If I just tab this back and look at this in isolation, this is just a regular factorial function, right? So I can just stick this regular old function inside my class, no problem. So now the question is, let's test it, right? Y'all probably by now know how big a fan I am of testing, so we'll do factorial. And some of you, depending on your other studies, may see the issue here. See if you can spot it. So I'm going to run this. And then this happens. It says, name error, name factorial is not defined. So, you might think, okay, maybe this is misspelled. These are spelled the same. I did my little highlighting trick, make sure those are spelled the same. So this is correctly spelled. Just do a little test here, right? What if I take it out of the class? Is this going to work? That works. So that works just fine, right? So why doesn't it run in the class? So whenever we're running a function or a method or accessing a property from within the class, we have to specify the name of the class in front of the attribute that we want to utilize, which is in this case factorial. So we would say factorial is an attribute of the stats tools class. So in order to invoke factorial in stats tools, we have to say stats tools dot factorial, right? So for some of you, and we'll just run that, for some of you, this might, well, presumably for many of you, list equals empty list dot append hello, right? So this kind of syntax where we have some list and then we dot append or whatever, call a method on it, right? So this is the same thing is happening for the same reason with this, right? So don't forget to specify the class and put a dot in front of the attribute you need. Cool. Okay, so this is how we can access our stats tools. Cool. All right, so let's build out. So I want to be clear about this real quick before I continue. this is what I'm doing is just building out a very simple class. All it is it's just going to be this name stats tools that's just going to encapsulate several functions, right? There are several sort of differing opinions on like what distinguishes a function from a method. You've heard me use the term method before. You'll hear about class methods, and the two terms in some cases get used interchangeably. But there's a useful distinction that I like to make, which is that functions, whether they're members of classes or not, a function, the way I use the word, takes in information as a parameter and returns information, right? So it doesn't specifically, it does not rely on information outside of it. And if we look, this function doesn't rely on any information outside of it, right? You might say, well, you know, if I had my number equals 4 and I passed my number, like, isn't my number outside of factorial? Yes, but it enters into factorial in the appropriate way, right? So even though this is not a local variable in the factorial function, we're passing it as an argument, right? This is different than let's say if I built factorial like this, right, where I have my number instead of n, and we'll just do my number here, right? So this is somewhat of a problem because something can come along and change this value, and now something that's necessary for the operation of this function is now different. And that's, I don't know, you know, you could, I think of a way to use that, but it's probably going to cause you more problems than it's worth. So yeah, so that's an example of what I mean by a function versus a method. So we'll look at methods when we get into the other classes as well, more formal methods. For now, I'm going to refer to these as functions, since, you know, the only relationship to the class that they're in that they have is that they're in the class. They're not, this class has no state that they're involved with or anything. Okay, cool. So let's build out another one. Oh, looks like we got a question here. When I print stats tools factorial 4, I still get an error that says stats tools is not defined. Oh, anyway, interesting. Does one say stats and one say stat? Oh, you figured it out. Good. That was it. Okay. Yeah, that'll get you. Yeah, no worries. Okay. Cool. I mean, I do that exact same thing all the time, and you know, it's just I've done it so much. I'm just like, this is probably a typo. But okay. All right, so let's do another one. Let's do permutations and combinations. So I want to give you an opportunity here. Yeah, write in your permutations function for a stats tools method. And you can do it from memory if you remember the permutations algorithm that you went over with Tovio. But I'll write it here, so I'll try to write it in plain text without it being too Pythonic. So it's in factorial, over n minus k, or n minus r factorial. And that's your permutations algorithm. So go ahead and write that up. And I admit I'm throwing you a curveball here. By the way, when I say write that up, I don't mean just like write it in, write it and copy it and paste it without testing it. I assume any code that you paste in, you've tested and verified that it's going to run. And I would expect that, if I was sharing code with somebody, I would have run it. If I'm sharing code with my coworkers, we're running it and checking it. So that's it's okay to run it to verify that it's working. You don't have to like make sure that it works just out of your own mind. We'll take a couple minutes for this. And I will post this really quick. I'm going to post this in. Here's our permutations algorithm. Also, if you get an error, feel free to share it. Yours works? Nice. Is it in your stats tools class? Nice. Nicely done. Okay, cool. So somebody has discovered the curveball that I'm throwing. Somebody's reporting an error that says name error, name factorial is not defined. So that's the error that we got before. So check out how we solved it there as well. And that's fine. To be clear, I don't mean to put anybody on the spot. I'm doing this as a curveball on purpose. So it's fine. Cool. Okay, cool. I want to give you all an opportunity to kind of do this. So I'm going to show a solution. So we can do def permutations. We'll take an n and k, and we'll return factorial n over factorial n minus r. Oh, I'm going to change that to r. So that'll be factorial n over factorial n minus r. Cool. Okay, so if I run this, let's do 10 and 1. Should get 10. So name factorial is not defined, and it's going to point at line 19, which is right here. So this is the thing, even when you're inside the function, or excuse me, inside the class, you still have to refer to other elements in the class with the class name in front of it. So even though factorial and permutations are both inside of the stats tools class, excuse me, if I utilize factorial, even inside the class and another function, I have to say stats tools.factorial. So if I run it like this, you can see now it'll return the correct answer. And I'm going to make mine into an int because this should only return whole numbers. So that's a little better. Cool. All right, let's do the same for combinations. So go ahead and start writing your combinations algorithm. If you don't remember it, I will put it right here. Cool. So that's n factorial over n minus r factorial times k factorial. And I suppose I should be explicit here. This is the lower term, that whole thing. So there's your combinations algorithm in Slack, and I'll give a few minutes for this one. I'll give a little longer for this one. I'm so sorry. I have a stray variable in there. I always call it K, but I'm trying to retrain myself to call it R. So it's just a a baked in habit. Apologies. Sorry about that. That should have been R, not K. All right, cool. Sorry, I just had to step out for a second there. Had to chat with my housemate about something. Okay. Let's see what we got. I'm just going to look through solutions. Feel free, if you're wrapping up a solution, go ahead and pop it in. Cool. All right, everybody caught my mistake about R and K. Good. All right, cool. Looks like people are onto this. I'll give my solution. I'm going to call this combinations. Sometimes I'll also call this choose, because sometimes we'll say like in choose K for combinations, or in choose R or something. So we'll call this in and R. We'll see if I can remember this time. And we'll return. So notice that first part is essentially just permutations. Permutations. And we'll do this second portion here. Actually, I want this again. Times in minus R yeah, okay, cool. So our combinations cool. I'll just like to check my work, make sure everything's behaving as expected, and we're good to go. All right. Cool. So we have a few useful tools that we can use for a variety of things, and they're all just bound up in this stats tools class, which is nice. So we can access them. This is kind of a longish name, but it's nice and descriptive, so that's fine. So I just want to demonstrate this. This is not a full object-oriented class. This is just a class with some functions in it. Doing this it's a very simplistic use of classes. It is valid code, so you can do this. Sometimes this can be nice if you have a few things that really kind of obviously go together, and you want to you want to like group them together under the same class name, this can be a really nice thing to do. So even though this is simplistic, I've used just really super simple classes like this, and it can be a good way to use classes. Cool. I talked about functions versus methods. Well, actually, that might come up again. Okay. Yeah, we'll get to those other things. Okay. So let's build out some more conventional object-oriented classes. Cool. Okay, so let's build a binomial class. So I'm just going to say class, and this is going to be more of a formal object. I'm going to follow object-oriented convention around naming, which is to use camel casing or to start the name with an uppercase, so capital B. If you're wondering why I'm doing that. If you don't want to do it, it's going to work the same either way. Doesn't matter. Yeah, we can leave the parentheses off. You will see sometimes there will be parentheses here. This does not at all work the same as it doesn't like define a region for parameters or inputs. It describes what other objects or what other object that this object would inherit from. Inheritance is a whole big kind of can of worms that we're not going to get into in this thing, but occasionally if you see parentheses after the class name, occasionally you'll see that. So in this case, it would work either way, but I'm going to leave them on just because that's kind of convention. Okay, so some of you may remember me talking about one of my favorite functions, dir. Let's get the directory of a list real quick. I'm sure that y'all have seen me do this at some point because I do it quite a lot. Oh, print is not a function. Print is a function though. There we go. So you've seen me do this, and then I'm like, okay, so this is how you can look up all the methods for a list, right? And then I say, but just ignore all the Dunder ones, the ones with the double underscores, these ones. We're not going to get, you can see there's a lot of them. And these are all built into Python. These are all built-in things that have special meaning in Python. So we're not going to get into all of them. We're going to look at a couple Dunder methods though. So this is, you know, I just wanted to tie this back in because I said I would earlier. I was like, don't worry about the Dunders for now. We'll talk about what those are later, and now it's later. So if you were curious, there's that. Okay. So let's see. Let's think of a problem first. Let's think of a binomial distribution that I might want to actually use. So let's say think of a binomial problem. So I need a series of Bernoulli events, which are an event that we can say has any one of two mutually exclusive states, and there's a probability associated with each of those. And the probability has to be consistent across trials, right? Trials also have to be independent of each other. So we'll say, we'll just go with the easy thing. Let's say I flip a coin 10 times. So 10 flips. What's the probability of we could calculate the probability of getting 7 heads or something, right? So we could say P that R trial equals 7, right? Something like this. So the way I want to use this, I'll just say 10 flips equals our binomial distribution, right? So notice I am going to put parentheses after it, and I'll get back to that in a second. So we have to take in some information. So this is what's called initializing the class, right? So I'm initializing this class right now. This is invalid code without that pass, sorry. So when we create a new instance of the class, we call it initializing it. So what's happening here is I'm creating a new binomial distribution from scratch here, right? And I could do this multiple times, and these could have, this could be one for 20 flips, right? I could have multiples of these, right? Okay, but we'll stick with 10 flips for now. So when I initialize the class, I want to have special logic that I run on initialization, right? So there's a special Dunder method called Dunder Init for initialize. So we'll say def Dunder, init Dunder, and this is going to take in an argument called self, S-E-L-F. The first argument has to be called self. And then from here, it's kind of up to us. It's parameter-wise, it's kind of a normal function. We can define what we want it to take in, right? So what pieces of information do I need for a binomial distribution? Well, I've got to know the number of trials. I've got to know the probability of success, which I'm just going to call P. And in order to do a PMF, which I'm the probability mass function, we need to know K, but we're going to worry about that later. Okay, so we need to take in the number of trials and the probability of success for each trial. So let's do that. So there's 10 trials, 10 flips. And since it's a coin, we'll just say it has a probability of success of 0.5, right? So for here, generally what you do in init, you can do a number of things. You can't return something from init, which is weird. But we'll get to that in a second. We'll get to sort of the workaround for that in a second. So init doesn't return anything. You can do whatever else you want other than return from init. Usually what you'll do is you'll set some initial states though. And what we're going to do is we're going to set some properties into the binomial class. We'll set n and p as properties. So these will just be really simple. We'll set, so we'll say self dot n equals n, and self dot p equals p. And while we're here, we can also, from n and p, we can infer the expected value. Who remembers how to do the expected value? Or if you don't remember, who can think what my expected value would be in this case, and how would you determine that? Okay, so I'll move us forward. So our expected value is going to be the number of events n times the probability of success. And you can think about it like, if I flip a coin 10 times, and I have a probability of success of 0.5, what's my most likely outcome, i.e. my expected value? Would be 5, right? What if I change the number of events to 20? Well, then our expected value would be 10. And then what if I change it back to 10 and then change the probability to 0.7? Well, then our expected value would be 7 heads or 7 successes out of 10 trials. Right? So if we multiply our number of events times our probability of success, we'll get our expected value. So we can just do that right now. We'll say n times p. And to be clear, you know, I mean, I know I just said this, but this is not the only thing that you can do in init, but this is often what you do. Let's set our variance is going to be equal to n times p, or actually that'll be our expected value. So I'll say self.expected value, even though it's shorter to say n times p, times 1 minus p. And then our standard deviation equals variance. And remember, is the standard deviation from variance? Yeah, cool, square root. So it'll be the square root of our variance. So I'll say variance to the 0.5. Oops. Variance to the 1/2. So that'll be our square root. Cool. So now I initialized my class. I saved that class into a variable. So let's play around with this real quick. So let's talk about what I know I just kind of wrote a bunch of weird code and didn't totally explain it. So let's kind of take a look at what's going on here. So I've talked about classes being containers or sort of ways of grouping state, which is stateful, or something that has a value. So something that has a state with things that describe logical processes like functions, or in some cases we'll call them methods. In this case, we'll call this a method. We call this a method because it sets state in the class, right? So it's going to set state in the object. So this self parameter, this is going to be our way of referring to the name of this function, right? So this is going to refer to itself, right? And not only will it refer to this body of code, but when we invoke this, if as it changes and as we manipulate this 10 flips variable, which is equal to this class, it will refer to that particular instance, that initialization, right? So self is going to refer to itself. It'll refer to binomial. It's binomial's way of referring to itself. So what I'm saying here, I talked about them being groups for state and logic to be grouped together. We looked at functions in the previous one, and we're looking at a method here. But what about stateful examples, right? So these are examples of setting state, where I say self.n equals n, self.p equals p. So what I'm saying here is that there's some property called n that I want to set. I want to call it n, and I want to set it equal to whatever n was here, right? So I can access that in here. So on line 45 here, I'm going to say 10flips.n. And let's just get this out of the way. We'll do the rest of them. P, expected value, variance, standard deviation. There we go. So obviously I don't really need to know the N and the P since I passed that in, I knew it up here, right? But it's now available to me where I can access the expected value, the variance, and the standard deviation at any time, right? So unless one of these changes, and we'll talk about what it means for one of these to change. Unless one of these changes, then yeah, I can access the accurate expected value, variance, and standard deviation, etc., which is kind of cool. Okay, cool. So let's get on to our PMF and CDF functions. Okay, so probability mass function. So this is going to be a method. I'm going to say def PMF, and we can ask ourselves, how do we want to use this? So I want to say 10 flips dot PMF, and then I need the PMF of what? We know the N and the P. We know the number of trials and the probability of success in each trial. So we need to know the probability. PMF is going to calculate the probability of some outcome. So that's our K value. So we'll say 7, right? Okay, so 10 flips dot PMF of 7. We want to calculate that. So if this were a function that I was just writing, a regular old function, I'd say def binomial PMF. We'll take in N, P, and K. And we write our logic in here. So in this case, all of my methods forever forward inside of this function, since I did this Dunder Init with self thing, the first argument to all of my methods is always going to be self from here on out, right? And this means it now has access to itself. It now has access to the stateful properties inside of it. I just realized I've been throwing that term around. Functions are sort of independent pieces of logic. Methods are logic that is sort of more entangled with the rest of the object, like that can read and set and initialize stateful properties, right? And properties are what we call the stateful elements, right? And these are kind of like variables in that they're sort of a name that points to a piece of data, right? So you can think about those kind of like variables. Okay, so PMF. So PMF is going to take in self and K. So notice I don't take in N or P. We already took in N or P, N and P up here, so we don't need to take them in again. So what I want to do, let's just, well, we'll kind of discover it. Let's do that. So I'm going to do return. And our algorithm here is going to be these are the N choose K. N choose K times P to the K times 1 minus P to the N minus K. And this will be one thing here. Cool. So this is our PMF, right? So this is how I'm choosing to write choose here. Sorry for the Weirdness. Okay. So I need that combinations algorithm. So combinations of n and k. Now remember, this is part of our stats tools class. So I'll say stats. Stats tools combinations in nk times p to the k times 1 minus p to the n minus k. Cool. So if I run this, just comment this out. Or actually, I'll leave that up there. Yeah, comment it out for now. Okay. So if I run this, notice I'm invoking it down here on line 54 where I'm highlighting 10 flips.pmf of 7. It says name n is not defined. And it's going to point at line 45 here. So it doesn't know what I mean by n, right? So you have to remember, you do have access to these things, but not just by default. You have to kind of bring them in. So one thing I could do is I have to refer to self.n and self, oops, not self.k, self.p, self.p, right? It's going to add kind of a lot of noisy code in there. So I'm just going to bring them in here. I'm just going to say n equals self.n and p equals self.p, right? So I'm just going to, what I'm doing here is just making two variables that are local to this function called n and p, and I'm accessing the properties that I set for the binomial distribution, self.n and self.p. I'm accessing those properties that I set in the Dunder Init method. All right. And that saves me from having to put self all in here and rewrite that code. Cool. So here's our probability of getting 7 heads in this case, right? Cool. And then one thing we could do, we have this, well, I'm trying to think of how I want to demonstrate this thing, but yeah, actually for now, let's just move on. Let's do another method. We'll do a CDF method. So I want to give you all an opportunity to write the CDF. Yeah, go ahead and write a CDF method on your own. The CDF is nice. It's just basically a numeric accumulator that accumulates probabilities within a range, PMF probabilities within a range, right? So the K value is sort of the upper limit, and it'll start from 0 to, if you do the CDF of with the K value of 7, it'll do from 0 up. It'll be the sum of the PMF values, where the K in each PMF is 0, then 1, then 2, etc. So it's pretty straightforward accumulator. I'll give you all an opportunity to hammer that out and make it work inside your binomial class, and then I'll show a solution. And do feel free, if anybody's got any questions, feel free to pop them in. Okay, cool. I don't see anything yet, but that's okay. Hopefully people had a good, oh, spoke too soon. There we go. Cool. Neat. We got a solution in there. Feel free to go ahead and post your solution if you like. And oh, we're just starting to get them come in. Great. That's great. Yeah, keep them coming in, and oops, I'll show my solution. So CDF, we'll take in self and cephl. I keep doing that. Self and K. And this is nice. It's just a really simple. It's just a really simple, sorry, I had a minor distraction there. Straightforward accumulator pattern. So we can say ACC equals, we'll start it at 0. And then I'll say for I in range 0 to K plus 1. We want to include K. We'll say ACC plus equals self.pmf of I. And we'll return ACC. Cool. So pretty straightforward here, right? And if I wanted to do the full thing here, right, I'd have to bring in self.in and self.p as well, but obviously we can just use PMF just like that. That's fine. So let's look at our CDF. Cool. There's our probability of getting between 0 and up to and including 7 heads for that. Okay, cool. So hopefully this gives you a basic idea of methods versus functions. You know, and just to clarify, I would consider these methods. If you look here, we're taking a reference to self, and we're referencing stateful properties from outside of this method, right? So it's interacting with the rest of the class, right? And to be clear, so this is at the beginning when I was saying object-oriented programming is built around this idea of setting and mutating state, setting, mutating, and referencing state within your functions. This is the referencing part, right? These are being referenced. They're being set in init. They're not being set in multiple places or, you know, mutated in multiple places. That's called shared mutable state, where you have a mutable state that's shared between multiple functions. I think at this point it's regarded as something to avoid like the plague, because it can cause, if you have multiple things altering the same thing, it can cause unforeseen problems and bugs and consequences. But this is that thing that I was kind of saying, you know, with the procedural programming paradigm that we've learned thus far, this kind of thing is taboo, if you want to call it that. It's discouraged. And in object-oriented programming, it's part of the thing. So there is somewhat of a contradiction here. However, notice this is certainly better than, you know, at least these properties are sorry, these properties are local to this class, right? So this is better than them being just global variables, which is, it's kind of like, you know, if these were global variables, you'd kind of be asking for trouble at some point. But yeah, a couple other notes here. If I wanted to give this, let's say, a new n value, or here, let's look at this. Let's look at our standard deviation. Standard deviation. Right, so this is the standard deviation for an n of 10 and a p of 0.5. We got a question here. Do the variables default to public or private to this class? Public, I believe. Yeah, and we're not going to be getting into whole public and private access yet. Well, not in premium prep. We'll cover that someday, but not now. Okay, cool. So we can look at the standard deviation. So this standard deviation bears on this n and this p. So if I change this to 1,000, I'll get a different standard deviation, right? So what happens if I say 10 flips dot n equals 1,000, and I print 10 flips n, right? So this is okay to do. So I just changed my, notice I just changed my my n value here, right? So the question is, did standard deviation change or not? We got to know. Anybody agree with the no? Anybody have a dissenting opinion? Two no's? Yeah, this is one worth thinking about. You know, think about it. Cool, let's run it. Let's check it out. And I'm just having you think about it just so you're kind of noticing, you know, what assumptions you might make. And cool, so our standard deviation does not change, right? So this is kind of a problem because our standard deviation is no longer accurate to our number of trials. It no longer reflects that. So things like this, you might, and this is kind of a silly example because, you know, I called it 10 flips and I'm changing the number of flips, right? I don't know, it's, you know, bear with me, I guess, but in this case, I might want to create a method for updating this value, right? Because if I update it in that way, like I kind of hose my data, it's kind of like, it's not gonna be what I, you know, it's all of this is no longer going to be accurate to this, right? I have a disparity in this data, right? I just broke my code. So I might, if I wanted to have the ability to change my n value at some point, I could create a method, let's say def new n, let's call it new n. We'll take in self and n. This is of course new n. Oh, I can't call it the same name as the thing. I'll just call it nw. wn. Okay, whatever. So I'm going to say self.in equals NWN, new n, and then I'm going to say self.init. Actually, what am I doing? I could just call self.init. Sorry. It's an extra step there. I'll pass in new n, and then for p, I'll just pass in self.p, which is the current value. So what it's going to do is it's going to reinitialize this, and it's going to run all of these, right? So this would be one way around that. Oops, and I said init. I'm sorry, I meant Dunder Init. So there are times when you can use init to sort of reinitialize new values, right? If you wanted to do that. And in my experience, it's generally that you'll use init inside the class like this rather than outside like that. Of course, this still. Oh, right, because I'm not calling. Sorry, I was like, wait, it's still broken because I'm not calling new n. And we'll do 1,000. Okay, so notice that this now returns none. Oh, I did this in a weird way. Print 10 flips dot in. Okay, there we go. So this sets the state. This prints out in, and then this prints out our new standard deviation. And we can see these have parity now, so that's okay. So for those of you who are looking at this and going, object-oriented programming seems confusing, it's a little bit, yeah, like, the idea is that you set and mutate state, and learning to keep track of that is even, this is not a complicated program. Learning to keep track of that is, whether you're thinking it looks complicated or not, it's worth focusing on and keeping in your mind, like keeping track of where your data is at, what's the state of your data, and making sure that you're not mutating things kind of laissez-faire all over the place, which can get really confusing, So this kind of pattern, and this is my opinion, and I'll phrase it as such, this kind of pattern, in my opinion, can be can create maintenance issues, right? And it's sort of a pitfall, a potential pitfall of object-oriented programming. And it's one of the reasons I don't prefer to start with it in premium prep. We start with procedural, which is a little more open-ended and a little more just smaller set of tools. But like, this is a different way of doing the same set of things. There are some organizational advantages. Everything's kind of nicely, like, kind of collected and sorted and organized, and that can be helpful. But there are some extra pitfalls to watch out for, such as this mutability issue, right? Does the state of something change, which is, where that state is a dependency of something else? And how do you make that other thing aware that the state changed? Because it's not going to do it. At no point will it assume to do it for you. You have to engineer that logic yourself, which might seem obvious or not, but I think it's worth saying either way, because if you kind of come into object-oriented programming without knowing that, making the assumption like, oh, well, if I change the n, then the standard deviation has to change. Like, yes, but you have to tell Python to do that, right? So just so you coming in with your eyes open, for context, this might be obvious. This is not my preferred paradigm. I tend to prefer procedural and sort of semi-functional coding in my own work. But I do use classes. I'll use them a lot of times, like I showed in that simple example. Sometimes I'll write a more formal class with an init, but I often will try to avoid setting state too much. And if I can avoid at any point ever doing something where I mutate state, I will. So like building a type that has mutable elements is something that I would consider doing, but it's sort of a last resort. It's like it makes sense in certain contexts, and this is Python's sort of easy way of serving that to you. But as a paradigm, as like this is the default way that like I do all programming, it's not my preference. It is the preference of some people. The reason we bring it up in Premium Prep is that object-oriented programming is really the dominant programming paradigm across languages. And all, I can't think of an industry that where it isn't. Well, I see a lot of functional and like blockchain stuff, but I don't know. Anyways, sorry. I can already feel the tangent coming on, so I'll spare you. But anyways, yeah, you will encounter object-oriented programming out in the wild, and we just want you to be aware of what it is, so that when you see it, you can start to make sense of it. And like I said, there are times when making a mutable object is fine, but in my opinion, not as the default. Okay, cool. So we went over a little bit, we went over quite a bit over our halfway point, but I wanted to get to this point before we get into our other class. So why don't we take a quick break, just reconvene at 7 after the hour. Yeah, sorry, 7 after the 20-minute mark of the hour. All right, we can start to get going again. I'll give people a second. If you can hear me, go ahead and take a seat, and we'll get ready in a second here. Cool. All right, let's do another class, and this will just kind of be, you know, a bit of a repetition. You know, it'll be obviously a different distribution, but so Poisson. So let's think of Poisson problem. Like if I um, let's say if I plant a garden and I notice that I have like expected, you know, I over let's say a 10 square foot area, I noticed that yeah, well, I just have to have an expectation here. So our expected, just trying to think of a good kind of intuitive problem. So let's just say like I plant some amount of tomato seeds and I notice like 7 out of 10 of them pop up. So yeah, so we'll say garden equals Poisson. So that'll be our lambda, right? So let's start with our Dunder Init function. Dunder Init will take in self and lambda, which is our expected value. And we'll say, we'll just set self.lambda equals lambda. We'll set our expected value, which is going to be just lambda again. Our variance is also going to be lambda. And our standard deviation is going to be the square root of our variance, which is lambda. So it'll just be the square root of our lambda. Cool. And let's do our PMF. So we'll say def PMF. We'll take in self and k. Yeah, we don't need to do that. We'll pull in lambda. We'll say lmbda equals self.lambda. And our Poisson PMF, I'm just going to write this one out rather than have y'all do it. Our Poisson PMF requires E, so we're going to pull that in from math. So I'll say from math, import E as E, and I'm going to use it just a capital E because Makes sense to me. And we'll return e to the negative lambda let's do this, e to the negative lambda times lambda to the k over, oops, let's do this, over stats tools dot factorial. Okay. And that should do it. And we can write our CDF. Self and k. And we can just do the same thing. ACC equals 0 for I in range k plus 1. ACC plus equals self dot PMF of I return ACC. Cool. Pretty straightforward. Okay, we can just hammer that one out. There is one more thing, and some of you may have tried this. I'll just say 7. Okay. Yeah, right. So I can say like 7 plants per square foot popped up or something like that. So that's my expected result. So if I forgot to mention this before, but let's look at this. If I just print this out, and this would happen if I printed just this out right there, but since I'm saving the Poisson distribution into the garden, if I just print this out, we're going to get a little bit of a problem. Garden. All right, so this is the printed value of garden. Day 11 lib.poisson object at RAM address. Not very useful, right? So one real useful thing, let's look at another Dunder method, and let's do this for both of these. If you want to have a way of representing your class visually, there's another Dunder method, which is called Dunder Wrapper. Def Dunder Wrapper. Doesn't need to take in, oh, sorry, it does need to take in self. And from here, so Dunder Wrapper just returns a string, usually an F string. And this will be how we want the class to be displayed. So I'm just going to say Poisson, and I'll say lambda equals self.lambda. And yeah. We could just do something like that, right? And I don't know if there's like a better way to display this or whatever, but you get to just write out this string, and that's what's going to be printed out every time it gets printed out, right? So you can actually see it. You actually have a representation that you can work with. So Dunder Wrapper is a really good one to know. Helps you keep tabs on things. You could print out all of these or whatever. You could include whatever you wanted in that F string. So you could do the same thing here. And then we could say, I don't know, how about our expected value? And we could do that for this too. So this can be another really useful one. Dunder Wrapper, when you want to give it like a way to actually look when you print it out. Cool. All right. So that's that. We've got quite a bit of time left over. I got a couple topics we could cover just really quickly. This class usually ends early, but we could go over a couple other things. And I'll leave it to y'all if you want to cover, what can we do? Well, let's just cover error handling. So here's just kind of a bonus topic. I think this is a fun one. Now, before, there's a reason I don't include this in like the official canon of premium prep material. I don't know, I might change that later. We might actually formally cover error handling. Before I show you, before we talk about error handling, I want you to bear in mind, this is the reason I don't talk about error handling at length or in other cases or include it earlier on in premium prep is I don't want to give people the idea that errors are bad. Errors are good things. They help you do your job better. So in general, if I'm writing code and I see a potential for an error to happen, I generally want to leave that open as a possibility. Not always, but generally I do want to, because like I said, that's going to give me useful information about how to fix problems. So you don't want to write code that's like error avoidant on principle. And I made the mistake with with one group in premium prep when I first started teaching. I was like, hey, this is error handling, so if you're getting an error, and then the rest of that cycle, I was, people were like, oh great, I never have to see another error again. And they're writing all this code that is like by default and on principle just enabled to throw errors, and nobody could figure out why their code wasn't working. I'm like, okay, so I need to make this clear. So just quick disclaimer, right? Error handling is awesome. It can save you work at times. It can make certain things really easy. But you don't want to lean into it too heavily, right? Errors are good things and they're going to help you, and yeah, they're great. All right, so, but let's look at it just in case we don't want to get errors. So let's think about something that's going to give us an error. Let's see here. Let's say adding, we'll take, what's going on? Oh, I'm not clicked in my, here we go. Hello divided by 5, right? So this is going to give me an error. I'll just play around with this. I should think of an actually useful example for when error handling is useful here, but let's see. So this is a type error. So the first thing you do when you want to handle an error is you get the error, and then you're going to copy the name of the error, right? So that's a type error, and I'll leave that there for now. So let's say I have some code that might error out. Should probably build this into a function like def may error, takes in a thing, and it divides the string by the thing. Now, strings aren't divisible by anything because they're strings and you can't divide a string, but should call this will error, but that's fine. So what I'm going to do is I'm going to say try. Okay, so I'm going to start with this try. And try just means here's some code that may throw an error. So in the try block, in the body of the try, I'm going to put the code that may throw the error. Why don't I do this? Why don't I, we'll have it divide by 10. And if thing is a string, then we'll get the error. So I want it to try this code. And if it throws an error, I want to say except the kind of error that I want to handle, which is going to be a type error. Often you'll see except type error as E or whatever, ERR for error, right? And this will capture the error message, right? So maybe we can log that error message or print it off or whatever, but if we want to be aware of it in some way. But this is going to catch that error and allow our code to continue to move on if we don't want it to just stop here, right? So sometimes you encounter a scenario where, oh, I just thought of a good example. Let's say I have a function where I want to square all the elements that are squarable, right? Squares list. Let's call it this. It'll take in a list, and we'll say for L in list, we'll try L squared. And let's do an accumulator. Oops. Accumulator list. And we'll say ACC list dot append this, right? And L squared may throw an error depending on if it can be squared or not, right? And let's look at an example of this. Print square list. We'll take in a list of right. Okay, so some of these elements are squarable and some of them aren't, right? Now I could do some type checking. That's what I, in general, when I think, oh, I could do error handling, I try to exhaust a few other options and I try to think, maybe I could do type checking, or maybe I could just handle this with regular conditions instead. But in this case, we can just use error handling, just another option. And we can say, after the end of this, return ACC accumulator list. So let's try that. Cool. So this executes without error. So maybe in the except. So notice except has a block of code indented under it. And in this case, I put a pass. I don't know if you recall, but at the beginning of class, when we first covered pass, it was near the beginning of class, I mentioned pass and I said pass is used as a placeholder. And aside from error handling, I don't know any permanent use for it in your code. This is the only time where that I know of where you actually use pass as like a permanent fixture of the code, not like pass for now and I'm going to come back and like fill this in later or something, right? And what it means in this case is just don't do anything. Like remember, pass is valid code that does nothing. You know, it exists because I can't put nothing in here. I have to put something in here, so pass is it. So in this case, it says try this, and if it throws a type error, just pass. Just don't do anything. Just whatever. Go on to the next thing. If I don't have this, obviously, I'll get a type error. And I'll get this. It'll say type error. Unsupported operand types for **, aka PAL, with string and integer. So it doesn't know how to raise a string to the power of an int, which is fine. I don't know how to do that either. Cool. So this will just ignore that error. But notice how pass has this block of code indented in it, because this is kind of like an if-else, right? Like if this doesn't give an error, then great. You know, you ran that code and it's going to do whatever it did. But if it does get an error, run this code instead, right? So this is the alternate. So this is kind of like the else, right? So maybe I want to just print, I could print ERR, right? Which is the variable that I named that I gave to the error string that it returns, right? So I'm going to catch the type error, name the error ERR, right? So it'll say unsupported operands for that. Maybe I want to add something to it. Or maybe I just want to say, I could write my own error, essentially. I could say, warning, L is a type of L, not an int. This will be a little dynamic message, right? So warning, hello is a class string, not an int. So I could do something like that. So this is error handling in a nutshell. Things to remember here. So the code that may throw the error goes in the try block. The error that you want to catch goes after the except, right? And we don't need this as error part. That's convention, is to like do like as e or as err, whatever. But you technically don't need it. And this will only catch type errors. So if I do something like print D, right? D is not defined, so that's going to be a name error. I'm still going to get that name error, right? So this allows you to be specific and say what you want to do for each type, right? So let's say I also want to accept name errors. I can have another accept, and I can say name error, right? Usually I'll just copy and paste it from the terminal here, pop that in. We can do that. Right, so this is going to give me a name error and has the same thing. In this case, I'll just print a name error. So I'm going to get that every time because I'm printing this thing that doesn't exist, right? So to me, I look at this and I'm like, you know, my code has errors in it. My thought is, okay, I'll fix the errors. And this is sort of like, there are times I'm not against using error handling, to be clear, but this can feel kind of like I'm just going to ignore the error, or instead of like writing in a way where it doesn't get an error in the first place, which is generally the preferable solution. But like I said, there are times when it's like, oh, okay, so in order to work around this error, I have to do all these other steps, or I could just catch the error and move on and do what I need to do. So there's times when it can really save you a lot of work and it's really helpful. But in my opinion, you should exhaust other options. You know, if you think I could use error handling here, go think about some other options first. Generally, alternatives are like type checking in some way. Like you can use type in various conditions to make sure that something is of a given type. Type errors are really really common one to want to get around. So, but if error handling is still easier, you can use error handling. So, yep, that's that. Oops, oh no, I thought I was able to see questions. Sorry. Oh shoot, somebody asked me to post the Poisson method. Let me do that right now. Sorry about that. That's the one I thought I posted. And these will be all on GitHub after class is over too. Cool. Okay, cool. Well, I'm not seeing any questions regarding anything, so I think we can wrap up early for today. Feel free to stay on if you have questions. Otherwise, have a good rest of your night. And I think I'm taking a Wednesday. I need to check the schedule if I'm on Tuesday or Wednesday, but yeah. Cool. I'll see you soon.